my name is Victoria and I'm going to talk a little about my PhD project, which is called Molecular Design of Coating based on recycled polystyrene with a reduced graphene oxide for protection and preservation of metallic art pieces. This is my work and we'll start with a brief introduction. There are many nanomaterials with properties that can help solve many problems in our world. Specifically, we work with graphene, a material that may not seem so new anymore, but many new applications are still being discovered because of this versatility. One problem to address in environmental pollution, such as acid rain, which increases strong acid in the environment. The level of acidity varies by area, but it can damage metal objects, especially outdoor metal sculptures in parks or historic sites. In Mexico, protecting their sculpture often involves highly toxic and expensive products. This project aims to create a material from recycled polystyrene, a polymer that pollutes in large amounts, combined with graphene properties. The goal is to develop a less costly, less toxic, and easily removable alternative. The main objectives are to synthesize the nanomaterial graphene oxide, which then be reduced to resemble pristine graphene properties and incorporate it into the polymer using ketone solvent. The goal is to characterize the material and test its performance to determine its viability. The method mainly involves synthesizing graphene oxide using Marcano-modified Homer's method. This meant putting graphite in an acidic solution to add oxygen groups to graphene sheets with an oxidizing agent potassium permanganate. After several washes to reach a pH of 5, the material is dried and we with graphene oxide, GO. Next, we perform a chemical reduction with hydrazine, which removes off of the oxygen functional groups to reform double carbons with the help of amino groups. This results in reduced graphene oxide, Re-GO. Polystyrene is treated with ketone solvents, which help turn it from a solid to a liquid state. We need it in this form to add the Re-GO into solution. Once the two materials are mixed, we apply them with a brush. We previously tried with other methods but didn't get the desired result, so we choose the brush application. This is effective because it's a common technique used by restorers. The samples were placed on sheets of mild steel and iron, and some photos were taken with an optical microscope to observe the arrangement of our material in the polymer. The images on the right are taken with a 40x lens, while those on the left are taken with a regular camera. We can see that as the concentration of Rio increases, the adhesion to the substrate improves compared to polystyrene alone. This is normal for this polymer because it is very fragile and easily detached. We also use a sample of the material commonly used, paraloid, which is an acrylic resin. However, its solvent, Helen, is highly toxic, and paraloid is expensive. We made a small sample of paraloid Re-GO. And the results, we first have GM image. We can see that both GO and Re-GO have a laminar structure with dimensions larger than a micrometer. However, in the case of Re-GO, we see some sheets that are somewhat damaged or possibly broken, but there are no clusters, no groupings. In Raman spectroscopy, we look for the characteristic signals of both materials. On the left, we see most noticeable difference between geo and graphite, including the formation of the D band, which is the attribute to defects in the sheet, and the broadening of the G band, which is related to the carbon double bonds. In the next spectrum, we can see the regio bands. We mainly look for the G band to be higher than the E band to initially confirm the reduction of our material. We are also continuing to work with that result to gather more information. Finally, in the spectrum of the right fog with a lot of noise, we can see the regio bands and a very characteristic peak of polystyrene. This shows the mixing of both materials interaction between them and structural rubber RP bond interaction, as both have aromatic rings in their structure that interact with each other without damaging their individual structures. We also took the geo and real samples without depositing them in the polymer to XPS. We look at the elemental percentage and aiming to see a decrease in oxygen signals in the regio, which we didn't observe. Since we don't have this equipment, we hope to do the analysis again with a positive material in the future. What we want from this material is for it to act a barrier against oxidizing agent or substances that could damage the metal surface, like water. So we are looking for hydrophobicity in it. A material is considered hydrophobic if it has a contact angle above 19 degrees. In this graph, we can see that almost all samples meet this criterion, except for those based on paralloid. We observe that as the concentration of Rio in the material increases, the hydrophobicity also increases. Due to the properties of graphene, in the case of sample C3, a higher value was not obtained because the surface was very uneven, making the use of the goniometer difficult. But we prepared more samples with a better surface, so we hope to get better results later. At the beginning of the project, a small test was done with a few layers graphene PLG. Applied in the same way on a sheet of iron, we can see the polystyrene alone easily come off the surface, but in the polystyrene FLG it does not. It has good adhesion and visually a good coating. Here are two things I would like to mention. One, we didn't continue working with FLG because the material concentration obtained are very small compared to RGO, 0.001 milligrams per milliliter of ELG versus the grams of RGO obtained. Also, FLG always needs to be in solution, whereas RIOR has very similar properties of LG. 2. Why is the more adhesion here and not in the sample sheets? Mainly is due to the mechanical anchoring. The sheet has been used for many years and its surface has been eroded over time, while the sample sheets are relatively new and have very smooth surface. This conclusion we discovered with restored. With this, I would like to conclude that this material has great potential for this application. We obtain it from a type of plastic that is already waste. The synthesis of the nanomaterial is done in a way that could likely be scaled up. But we are still conducting many analyses and tests that I didn't have time to include in my poster. For example, a week ago we took the samples to an agent's chamber to see how the material reacts to temperature and radiation exposure. We also need to conduct a more in-depth analysis of the results we have so far, and aim to publish an article as soon as possible. Finally, I include some of my references. There are no minimizing borderos of anyone. And thank you for my advisors and my college family and friends. And thank you very much for listening to my work.